and to have certain proofs about properties. Where from this grammar came suddenly? That's a question. So till now, what we have studied is finite automata model, and that is an abstract machine, right? That we have studied. And also, using that finite automata model abstract machine, we have learned something like the languages that they accept, and we name those languages as regular languages. So till now, you have some what are regular language. You know what are regular languages, and you have an idea of what a language. Define it's a set or specific type, right? Now, we'll see. What I will try to do is I'll try to classify this. There are several other regular languages. So people who are going through the book, people who are and they are going through the book, they would be coming through uh, this these classes of languages. How many classes of languages are there, and why we classify them? And from that language perspective, I'll get into grammars. Right. So today's topic will be grammars, and from now on we will be talking on grammars. But I want to enter into grammars from the perspective of languages, because ultimately grammars are generators of languages. Got my point? So if I don't go through languages and just talk about grammars, it's a very simple thing. A grammar can be formally defined as a four tuple VTPS. There is nothing more than VTPS, right? It's extremely simple. V stands for non-terminals. T stands for terminals. P stands for set of rules of production, and A stands for the start symbol. Now, understanding G is nothing but VTPS is extremely simple, right? Now, what are these non-terminals? Non-terminals can be perceived as something that can be further reduced to a series of terminals eventually, right? So we say that actually this set of rules called the set of production rules, these set of rules are of the form alpha can be reduced to beta. Very simple. Where alpha, beta are strings from V union T star. Now, by now you know what is a star operation, right? So V's are terminals, non-terminals, and T's are terminals. So what is T? T is a subset from the alphabet. So when you are talking about a string of the language, you are actually talking about a sequence of T's, right? And those sequence of T's can be actually derived from starting from S, an application of several production rules, reductions of several alphas to betas that may contain alphas and beta both may contain instances of V's as well as T's. Now, without talking about all these things theoretically, let us quickly come to an example language. Say a language of any number of zeros followed by any number of ones. 0m1 mn greater than equal to 0. Now, did you see this language before? Any number of zeros followed by any number of ones. If I talk about this in English, it turns out to be a very simple automation, right? Any number of zeros followed by any number of ones. As simple as that. If we talk about from the machine perspective, it is any number of zeros followed by any number of ones, and you accept. This language is written like this, and if I use a regular expression for this, what should I write? 0 star 1 star. Simple. So this is a language. This is a machine representation. This is a regular expression representing this set, the language. Simple. Now let us use this VTPS form of definition to see that how this same language can be generated by the newly introduced notion called grammars that I newly introduced. So let us talk about this language. It is any number of zeros followed by any number of ones, and that any is justified by m and n. See, I have written m here and I have written n here, right? I have written m here and I have written n here. So m and n together justifies the term any number of zeros followed by any number of ones. Agreed? I want to listen a yes from you because I cannot see you. I am in a very difficult position to see whether actually you are listening to me.
Yes, sir. Yes, sir.
Okay, okay. So till now things are very simple, right? Now I will keep things simple today. So let us talk about let us. So what did we see? We saw a very simple machine description of the language. We saw a regular expression for the language, and we saw how the language can be written format. Now let us talk about that VTPS thing, that grammar thing that can be written in this form, right? So s. So let us say that okay, v contains v is nothing but s. We do not need for this very simple any number of zeros and any number of ones case. We do not need any more s's. It's very simple. T is a set of terminals that is 0 and 1, that is equivalent to that is equal to sigma, the alphabet. Okay, and alpha, the alphas and betas, the set of productions looks something like this. I design something like s goes to 0s, then I design something like s goes to s1, and I design something like s goes to epsilon. Now see, each of these is nothing but of the form alpha, some alpha goes to some beta, right? This is some alpha, alpha I, beta I. This is some alpha going to some beta. Each and every production. So this is production 1, this is production 2, this is production 3. Each and every production is of the form alpha goes to beta, where alphas and betas contain symbols from both V and T. For example, this alpha contains a single symbol from V because your V contains S. This beta contains both an element of T and an element of V. So that's why we say that alphas and betas are elements of V union T star. V union T star means it's alpha and beta can be epsilon also. That is justified by the last production. So what we have three productions, right? S goes to 0s, S goes to S1, and S goes to epsilon. If we apply these three productions in 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 any number of ways and in any number of times, and if we can derive strings that that stay in this language, and if we can derive strings that stay only in this language, only those strings that are member of this language, and we derive no other strings that are not a member of this language, then only we can say that okay, this is a grammar for the language 0m 1m. Got my point? So let us apply. Let us check for some string. It's very obvious. Let us check for some string. Say any number of zeros and any number of ones. 3 zeros and 2 ones. So what do? We start at s. We apply. The string starts with a 0, so we apply this production 0s. Then then this we reduce this s with again a 0s. Then we reduce this s, so we are applying production 1 only till now. Production 1 again we apply 0 0 0 s, right? We apply production 1 only, and then we apply production 2. So we have 0 0 0, then s1, then again we apply production p2, and we have 0 0 0 s s1, right? So this s goes to s1 again. This s goes to s1 again. So s11, sorry. So you have s11, right? and then we apply P3. What is P3? S goes to epsilon. So we apply P3, and we have 00011. This is called a vanishing production. S P3 is S goes to epsilon. So by applying P rules, P1, P2, and P3, accidentally it seems that we should be applying P1s and then P2s and then P3s. No, there is no rule that says that you have to apply the productions in order, in some order. No, you can apply any production at any point of time to reduce the some left hand side. So this was some left hand side that got reduced to some right hand side, right? This was some left hand side that got reduced to some right hand side. So this way you can actually use grammar rules to derive strings of the language. And then you have to check whether accidentally application of any or a combination of such rules derives any string that should not be a member of the language. But it is a pretty simple language and a pretty simple grammar to represent that. And we see that, okay, this may be one such language of, one such grammar of the language of any number of zeros and any number of ones. Now let us take another example, 4 zeros and 4 ones. Are you listening, guys? Are you there?
Sir, yes, sir.
Yes, sir.
Sir,
So
could you scroll up once, sir? Actually, there is the lag is. I missed one thing out of the lag, sir. It's
yes,
zoom out. Yes, sir. So what are we
yes.
considering as the S, sir?
S
The
is the start symbol.
okay, there is no specific start symbol, like because in this case we're
It's
starting with zero, right? So it should be zero.
no. S is V. S is an element of V. It's a non-terminal symbol. If you think of a tree, the root of the tree is always a non-terminal symbol, right? If you are to
Yes.
derive symbols by a tree representation, so what I'm doing is S goes to 0S, then this S goes to 0S, then this S goes to 0S, then this S goes to S1, then this S goes to S1, right? Right? Did you get the picture? Then what I'm doing is I'm collecting these as leaves like this and getting a string 00011. And finally I applied S goes to epsilon and and try to eliminate S. So that essentially you have a string 00011. Got my point? So this can never be a terminal. These are terminals, zeros and ones. So terminals are nothing but the actual components of the string. So this is a string. The actual components of the string that you should finally land up with are the terminal symbols, right? So that's why I told that the terminal, the set T denotes a set of terminals. The set V denotes a set of non-terminals. And in this case, in this example, we have only a single non-terminal S. And with a single non-terminal, we can design a very simple grammar for this very simple language. We do not need other non-terminals. Is it clear? Yes or no?
Yes, sir.
Done?
Yes, I got it, sir. Yes, I got
Yeah, yeah. Absolutely clear? Yes or no? Okay.
it. So
So
clear.
yes.
Yes,
So
yes, sir,
let us
clear.
take another example. Now my question is 4 zeros and 4 ones, equal number of zeros and equal number of ones. Is it a member of any number of zeros and any number of ones? Talking otherwise, is it a member of 0 star 1 star from the regular expression perspective?
Yes, sir. Yes, sir.
Yes. Yes. But your grammar was S goes to 0S and then S goes to S1 and then S goes to epsilon. You had three productions. Now, my question is, does these three productions is a combination of these productions capable of generating strings that are equal? Because you are telling that we are designing a grammar for any, right? Now, is this grammar capable of generating strings that are always equal? See, try to understand my question. I am asking you, is this grammar capable? So we have seen that this grammar is capable of generating any number of zeros and any number of ones. Done. Now this is a string that is also a member of any number of zeros and any number of ones. The equality being just by chance, right? So if m and n are any, at times they will be same, right? How did you define any? We define any something like 0m, 1n, mn greater than equal to 0, right? So for 0, for m equal to 0 equal to n, they are equal. For m equal to 0, n equal to 1, they are not equal. For m equal to 1, for n equal to 1, again the number of zeros and ones are equal. For m equal to 1, n equal to 105, for example, again the number of zeros and ones are not equal. So being equal are very normal, and it occurs at times. So this grammar is also capable of generating these equal number of zeros and ones, but from the perspective of the fact that equality here is a part of any, right? So equality is a part of any. So if I say that is this grammar capable, is this grammar capable of generating the same number of zeros and ones? The answer should be no, because at that point of time I'm expecting the grammar to generate exactly the strings that have the same number of zeros and same number of ones. So at that time I am seeing the equality not as by chance, not as in intervals, or not as a part of the any problem. When I'm asking the question that is this grammar capable of accepting strings that have equal number of zeros and ones, then I am actually asking this question that whether this grammar shall accept only those strings that have equal number of zeros and ones. And clearly the answer is no, because this grammar is capable of generating any number of zeros and ones, right? So I can show, or we can show, that by applying, this is P1, this is P2, by applying number of P1s more than number of P2s, we always have number of zeros more than the number of ones, and applying P2s more than the number of P1s will actually generate more number of ones than zeros. So this grammar is not capable of generating strings that always have equal number of zeros and equal number of ones. Did you agree? Yes or no?
Sir, could you, sir, I did not really get this point, sir. Could you explain?
You did not really get this. Okay. Are you concentrating?
Yes, sir. Sir, actually, I got confused, sir, with the P1 and the like.
Yeah, you got confused, right? Okay. Okay. So shall I go a bit slower?
So, sir, I got the part where we can that O and like sorry 0 and 1 cannot be like it's not only accepting the same number of zeros and ones. It like if it is there, it is there. That's a subset of the
Okay. So
acceptable language.
let me say 0n 1n. That means always zeros and ones are same is a proper subset of any. Do we agree? Yes or no?
Yes, yes. This is what I was saying, sir.
This is what I was saying,
Yes.
and this is what you were saying. So actually, what I was saying and what you were saying are same. So why did you say that you didn't understand? You
So I
understood?
didn't understand the P. So the PY, sorry, P1, P2. So that part.
Okay. So let us talk about this Venn diagram. Actually, you took me back to that Venn diagram, and I was actually avoiding, because once I draw this Venn diagram, my fingers are very excited to extend that Venn diagram to the classification of languages that I'm very hardly trying to avoid in this class, right? Okay. So I was actually talking about this any number of zeros and any number of ones case, right? And we talked about a grammar, a very simple grammar. S goes to 0s, S also goes to S1, and S goes to epsilon. So this grammar is capable of generating any number of zeros and any number of ones. Now that in certain cases that any becomes equal is a subset, right? Now my question is, if I ask you to give me a grammar for this subset only, give me a grammar for this subset only. If my question is, give me a grammar that should accept this subset only this subset, only is very important, right? This subset. If I ask you that give me a grammar that accepts only this subset, then if you say that, okay, sir, we had derived a grammar for this, then your answer will be right or wrong. Remember the part only. This is very important. Now this grammar gives you this whole portion, right? This grammar gives you this whole portion. So this grammar is capable of generating this subset. But this grammar also generates other things other than this subset. It also generates this portion, right? Now I am asking, give me a grammar that generates only this subset. I do not want that yellow portion. Then your answer should be that no, sir, this grammar, the grammar that we are talking about is giving me the whole thing. Now, if you require only this portion, and not the yellow portion, then this grammar is not the right grammar, because this grammar is capable of generating a bigger subset, right? Got my point? Now, is it clear?
Yes, sir.
Yes. So now, if it is clear, now the equal case. So let me write the language. So the equal case should be 0n, 1n. Now I have replaced the m with an n greater than equal to 0. So this is the language that I'm talking about in the middle, right? Now this language is also generated by this grammar, but this is not the only language that is generated by this grammar. This grammar also generates the yellow portion. But now my question is, give me a grammar that generates only this and not the yellow portion. I want a grammar that generates only the equal case and not the yellow portion, right? Now this is a special language, and you have studied from the previous classes that this is not regular. Is this regular? Is this language regular language?
So not regular, sir.
No, sir.
Not regular. You are sure?
Yes,
Yes.
sir.
Yes. Okay. So can you please switch off your microphones? Yes. Okay. So this language is not regular. So similarly, there should be, if there is a hierarchy of languages that may be regular, that may not be regular, similarly we should have a correspondence in grammars also. So the grammar that we had been talking about is not capable of generating this language, only the strings of this language, because the grammar that we had been talking about was essentially regular. I'll show you how it was regular. So we need a grammar that generates only this language. Now forget about regularity altogether. Forget about this particular thing. We have a problem in hand and we need to generate a grammar with the VTPS notation. Right? We need to have a grammar for this. Now, what is this 0n, 1n? It essentially says that if there is a fulcrum, the left hand side of that fulcrum should balance the right hand side of the fulcrum. It's a balance parenthesis problem in terms of zeros and ones. Do you agree? 4 zeros, 4 ones. It's nothing else. Do you agree? Yes or no? So
Yes, sir.
it has strings of the form same number of zeros and ones. 4 zeros, 4 ones. 0 zeros, 0 ones, epsilon. 1 0 1 1 0 1. 2 zeros, 2 ones. 3 zeros, 3 ones. So it's a language. The language contains strings of this type. It's an infinite set. This is the actual language that we are talking about. If we say that, okay, this is the language. This was in notation form and this was the expanded form, right? So the design of the grammar is inherently recursive, and it is recursive in the middle. See, don't misunderstand me. This grammar is also recursive. I had shown you in my lectures how actually we perceive recursion and we construct regular expressions with recursion. So this is also recursive. But what I'm talking about this, here we need to have the recursion in the middle. Recursion in the middle means whenever I add a 0 on the left, I should also be adding a 0 on the right, adding a 1 on the right. So very simple grammar rule. S goes to 0, S, 1 and epsilon solves your problem. So this is a grammar that always generates same number of zeros and same number of ones. Okay, the tree view, somebody asked for the tree view, 0, S, 1. I apply production P1 once. Then I apply production P1 again, 0, S, 1. Then I apply production P1 again, 0, S, 1. So remember, this S is always reduced to 0, S, 1. Because that was the production. S goes to 0, S, 1, right? Now this S is again getting reduced to 0, S, 1. Right? Agreed? Now, what is the typical difference between this grammar and the previous grammar? The previous grammar was reckless. It was not worried about the count on the number of zeros and number of ones. Any number of zeros and any number of ones. That is what I meant. But here, strictly you are following that. Okay, if I so S, so let me write it again. S goes to 0, S1. So S on the left, if I substitute S somewhere in the middle, it should be 0, S1. That means I take a 0 on the left and I take a 1 on the right of me, if I am S. So let us start with S. So I have only one production like this to expand the sentential form. So it should be 0, S1. The time I take a 0, I'm always sure that I always take a 1 on the right. Then again I expand. S goes to 0, S1. Then again I expand. S goes to 0, S1. So if I am talking about the string 0001111, then I would apply S goes to epsilon and collect the leaves of the trees like this, so that you have 0001111 as the string. Now remember, you always have 0 and 1 in as the strings by virtue of the character of the production. The production always takes care of the fulcrum in the middle and generates zeros on the left and ones on the right, exactly one at a time. So one, it will generate 1 1 for 1 0 on the left. It will again generate exactly 1 0 for 1 1. So the count is always kept intact. Right? Now my question is there a difference in the structure? So the previous grammar was S goes to 0S, S goes to S1, and S goes to epsilon. So this was for any number of zeros and any number of ones. That has a very popular regular expression also. And now we are talking about the equality case. So we have S goes to 0, S1. I am binding the number of ones and zeros always. And S goes to epsilon. Is there a difference between these two grammars? Right? Is there a difference between these two grammars? Of course, they are different because this is generating this particular subset 0n, 1n, and this grammar is generating the whole set, right? Any number of zeros and ones. Of course, there is difference in their functionality. Now, I am asking you, do you perceive a difference in their structure? The structure of productions. Anybody there? Knock, knock, knock. Anybody there?
Sure, like they have lesser rules in case of the same number.
I previously said that as long as the number of rules are finite, it doesn't make sense whether you have 10 rules or you have 100 rules. You need to have finite set of rules, right? So one grammar may have 100 rules and one grammar may have 1,000 rules. As long as you treat hundreds and thousands as countably finite numbers, there's no problem. So that is not a criterion for difference. I am asking you, is there a difference in structure? Okay, let me rewrite this grammar in a more understandable form so that the structure, the difference in structure becomes more evident. Right? The left side grammar. So it was 0 goes to 0s, s goes to s1, and s goes to epsilon. I am just rewriting this grammar right now. What I do is I write s goes to 0s or s goes to epsilon. I take care of this the very first time. Now s goes to 1a. I introduce a new non-terminal called a. S goes to 1, a goes to 1a, and a goes to 1. Now this is the same grammar equivalent to this grammar. I have introduced another non-terminal, right? As long as the set V is finite, you can have any number of finitely countable non-terminals. It doesn't matter. So in this case, V was S only, and in this case, V is S and A. Both are finite, no problem. In this case, T was 0 and 1. In this case, T is also 0 and 1 because we intend to generate strings on zeros and ones. So T remains same. Got my point? And here, in this case, the set of productions P, in this case, the set of productions, size of set of productions was 3. I had 3 productions. And here, the set of production size is 1, 2, 3, 4, 5, 6. So as long as 3 and 6 are finite numbers, doesn't matter. But they are equivalent in their working capability. So if I treat this as grammar G1, this as grammar G2, both are equivalent. Now what I've done is essentially I have taken all the non-terminals of the right hand sides to be the rightmost symbol. See, in this production, S is a non-terminal, and if S occurs on the right hand side, it occurs as the rightmost symbol. There are 2 symbols of the right hand side, 0 and S. So the non-terminal is the rightmost symbol. Here I have 2 symbols, right? The non-terminal A is the rightmost symbol. Here I have 2 symbols, and the non-terminal A is the rightmost symbol. So somewhat I have managed to configure this grammar that was a bit haphazard. There was no fixed structure to some fixed structure, and that fixed structure is, if I have terminals, non-terminals on the right hand side, it should be right, or else I can have only terminals. So this grammar gives you a structure, right? So this grammar gives you a structure that alpha arrow beta where alpha, and also observe that the left hand sides is always of finite size 1, right? So you say that alpha mod alpha is 1, and beta looks like beta, that means the right hand sides of the productions, all these are the right hand sides of the productions, looks like it should be a series of terminals followed by a non-terminal, if any, or if there are no non-terminals, it should be a series of terminals. Now what I have done is I have overlaid this concept here and transformed grammar G1 to G2 so that you have a specific fixed structure, the same grammar for generating any number of zeros and any number of ones. Do you agree? Yes or no? Are you there? Knock, knock, knock.
Yes,
Are you
sir.
there, guys?
Yes.
So I have transformed G1 that was lacking some specific structure to a grammar G2 that works like the same thing, and put a structure there, and that structure says the left hand side is always of size 1, and the right hand side has a form. If you have terminals, they should occur first, followed by a non-terminal as the last symbol of the right hand side. Done. And if you don't have a non-terminal, then it should only be terminals. So all the productions agree. We all agree, right? So the first production is 0s, and S is on the rightmost. S occurs as the rightmost symbol. S goes to 1a. A is the rightmost symbol. S goes to 1. Okay, this is of the form of some non-terminal going to some terminals. A goes to 1A and A goes to 1. Right? Now, having said that, so let us again come back to the problem of any number of zeros and any number of ones versus same number of zeros and same number of ones. Right? So let us write down the grammar like this. So the grammar is S goes to 0S or 1 or epsilon. S goes to 1A, right? A goes to 1A or 1. How many productions? 1, 2, 3, 4, 5, 6. There are 6 productions. And all of the productions are of the form that the right hand side are either non-terminals, or if they at all have a terminal, that should be the rightmost symbol. Done. So I have put the grammar in some structure. Now, what was the grammar for same number of zeros and same number of words? It was 0 is 1 epsilon. And nothing can be more done to this very simple grammar, or nothing, no more simpler structure can be overlaid to this, because it is already simple. And it says that, okay, the left hand side is 1, but the right hand side, uh, there is no restriction on right hand side, has no restriction. Right hand side can be anything. That means right hand side is anything from V union T star. So there I say that it has no restriction. It means that this grammar has some restriction. The grammar on the left hand side has some restriction. What is the restriction? It says that people are trying to define how beta should be like. People are trying to define how beta should be like, right? So people are defining that, okay, beta should be a series of non-terminals like this, or if at all it has a terminal, it should be a series of terminals followed by a non-terminal. If at all it has a non-terminal on the right hand side, or the right hand side can be simply a series of terminals. So they impose that beta should be like this and beta should not be like this. Similarly, in society, you say that a student should be like this, studying 18 hours a day. A student should not be roaming about in streets. These are restrictions in life, right? Similarly, we say that this grammar has a restriction on how beta look like. And if we define restriction like that, here we say that beta has no restrictions. So immediately we are in a position to compare these two grammars in terms of structures. So they are structurally different, in a sense that here beta has a restriction, and it is said that it should be series of terminals like this, or if it at all has a terminal, it should be the rightmost symbol of the right hand side, that is beta, and it should be preceded by terminals, and the left hand side is 1 always. So these are the two rules, or these are the two rules of how alpha and beta look like. And here, this grammar for equal number of zeros and ones, the left hand side should be 1 as usual, but beta has no restrictions. Now come back to your old concepts. I hope things are very simple as of now. Please try to concentrate, because we are going to delve deeper into deeper concepts, into deeper recursions, deeper generations, right? So if you are not paying attention, next classes will be very, very boring. I didn't like boring classes in my student life, so I think that you should not be taking yourself to a position that classes becomes boring, right? So try to concentrate. So having said that, you have a knowledge that this is a regular language, but this is not. You had proved with pumping lemma that this is not a regular language, non-regular, right? And you know that this is regular. Any number of zeros and any number of ones is regular. Same number of zeros and same number of ones is not regular. So obviously this grammar that I'm talking about is a regular grammar, and this grammar that I'm talking about is a non-regular grammar. Right? What is this called? Does it have a name? Yes, it has, and it is called a context free grammar. Now, why it is called context free, I'll come in the next class. Please check whether whatever I talked about in today's class was understandable or not. Because if I get a positive signal from your side, then I will go back into the computability theory and I will talk about how these grammars, these machines, and these recursive functions join hands in a sense that they perfectly claim their own generations as 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 and they define computability theory in general, right? So any problem in understanding what I talked about? Yes or no?
No, sir.
Clear? Absolutely clear?
Yes, sir. Yes, sir.
Yeah. Okay. So I end today's class, and we'll be meeting tomorrow at 11:30 from 12 to up to 12:30. Please check if your friends are interested to join, and ask people who are only interested, they should be joining my class, and people who are not interested should not be joining. Done.
Okay, sir.
So
Thank you, sir.
whoever is present in today's class, um, um, do we agree to have a class tomorrow at 11:30? Yes or no?
Yes, sir.
Yes, sir.
Yeah, thank you. Because I could not take class on Tuesday. I was so busy, and also I missed yesterday's class. So I made up a class for Tuesday by taking class today, and tomorrow I'll take a class at 11:30. Please open up your minds. Try to concentrate. Open up your brains and just listen to me and look to the board. You will understand everything, I hope. So today's class was understandable. Yes or no?
Yes, sir.
Yes, sir.
So
Yes,
are
sir.
you in a mood so that I continue for 10-15 minutes more, or shall I leave you?
Sir, actually, a lot
Yes.
of us have like limited net, sir. So we've had
Okay.
already had 4 classes today, sir.
Okay. So tomorrow I think I'll be getting some more time, right?
Yes, sir. Yes, sir.
Okay. So what if I start class at 11 so that I can get a solid 2 hour class?
So it's fine, sir, I guess.
Okay. So tomorrow let us start at 11. Okay. Okay. Bye.